Hello and welcome. Our lesson today is on section 5.4, exponential functions, differentiation and integration. So we're going to talk about and define the natural exponential function and then talk about how to differentiate and integrate different variations of it. Okay, so the natural exponential function is the inverse of the natural log. So it is e to the x. And so y equals e to the x if and only if x equals the natural log of y. This if and only if you want to start abbreviating it as IFF, you can do that. Sometimes it's put in quotes, sometimes it's not, but you're welcome to use that abbreviation. If we graph the natural log and e to the x next to each other, we see that in fact they are reflections over the line y equals x of each other, which is great. The natural log has the y-axis as an asymptote, and e to the x has the x-axis as an asymptote. And of course, when we compose them together, the natural log of e to the x is going to equal x, and e to the natural log of x is going to equal x because they are inverses. All right, next theorem. This theorem is just a reminder of exponent rules. So remember, when you have the same base and you're multiplying them, you can add the exponents, and when you have like bases and you're dividing them, the exponent is the difference between the two exponents. Some properties of the natural exponential function: its domain is all real numbers, its range is all positive y values, or whatever the output is, whatever variable, but y in this case. And we know that this function is continuous, increasing, and one-to-one on the entire domain. It is also concave up on the entire domain. And if we look at the graph, we see that the limit as we go to negative infinity is 0. So it has the x-axis as an asymptote, and it goes to infinity as x goes to infinity. And the graph here has 4 key points that are helpful when graphing transformations of e to the x. All right, now let's talk about calculus, derivatives. So the derivative of e to the x is e to the x. It's the easiest derivative. It's awesome. It's great. It's wonderful. And of course, we have the second variation here, which is my chain rule. So if we have e to a function of x, then that's going to be e to that function times the derivative of that function. All right, let's do some examples. So first example, let's find the derivative of e to the negative 3x. All right, so here we go. So if we're going to use that second rule, we're going to say, well, this is e to the negative 3 over x times the derivative of negative 3 over x, which we can also write as, I'm going to rewrite that actually now, as negative 3 times x to the negative 1. And then we get our good old friend, the power rule. So we have e to the negative 3x, and then we get negative 1 times negative 3 x to the negative 2. And simplify that, we get 3, the negatives can cancel, so then we get 3e to the negative 3 over x, all over x squared. Great. Next example, we're trying to find the derivative of e to the 3x over e to the x plus 1. And so in this one, we're going to do the good old friend quotient rule. So the quotient rule says take the derivative of the numerator. So we get 3 times e to the 3x using chain rule times the derivative of the denominator, and then minus the numerator, e to the 3x, times the derivative of the denominator, which is just e to the x, all over the denominator squared, e to the x plus 1, quantity squared. So then I'm going to go ahead and distribute. So then I get 3e to the 4x, because 3x plus 1x is 4x, plus 3e to the 3x minus e to the 4x, all over ex plus 1, quantity squared. And then I'm going to go ahead and combine my like terms. So then I get 3e to the 3x plus 2e to the 4x, all over e to the x plus 1, quantity squared. And typically when we're working with exponential functions, we factor out any e to the x functions or e to the x factors. So then I'm going to factor out e to the 3x, and I'm going to be left with a 2e to the x plus 3 over a e to the x plus 1 quantity squared. Great. Next example. Find an equation of the tangent line to the graph f of x equals 2 plus e to the 1 minus x at the point 1, 3. All right, so remember tangent graphs, we're finding the derivative. We plug in the x value, and that is the slope of my tangent line. Okay, so first start by finding the derivative of this. So the derivative of this is going to be, well, that's a constant, so that's fine. So we get e to the 1 minus x times, and then the derivative of that exponent is negative 1. So then we just get negative e to the 1 minus x. Okay, so then I'm going to plug in my x value to find the slope. So f prime of 1 equals negative e to the 1 minus 1, or e to the 0, which anything to the 0 power is 1. So there's my slope. And I'm going to use good old friend point slope form. So reminder, point slope form is y minus y1 equals m times x minus x1, where these are the coordinates of the point you want to go through, and those are going to be 3 and 1. And then we found our slope was 1. And so, oops, did I mess up? Our slope is negative 1. Yeah, negative 1. I did mess up. Okay, and then y and x get plugged in there. And then if you like slope-intercept form, let's go ahead and do that. And add my good old friend 3, so I get y equals negative x plus 4. So that would be the equation of the tangent line. So my tangent line is just going to touch my function at the point 1, 3. Here's the graph of it, if you want to look. So we go through the point 1, 3. This equation has a slope of negative 1, so this would be my y equals negative 1 plus 4. Negative 1x, excuse me. Okay, next example. I should have put that graph a little higher. Show that the standard normal probability density function, which is 1 over the square root of 2 pi times e to the negative x squared over 2, has points of inflection when x equals plus or minus 1. So remember, inflection points, we need to find the second derivative, okay? So let's go ahead and work on that. So my function, I'm just going to rewrite it over here. And when I find my second derivative, I've got to go through and find the first derivative. Luckily, I don't need to use product rule quite yet, so I have my constant in the front. Yeah. 2 pi, there we go. And then I got to use my good old friend, the chain rule. So the derivative of the exponent is just negative x. And then I have times e to the negative x squared over 2. Great. And so now let's go ahead and find the second derivative. Okay, so the second derivative, I have 1 over that square root of 2 pi. And then I'm going to have to use the product rule here. So the derivative of my first function is negative 1 times my second function, e to the negative x squared over 2, plus my first function, negative x, times the derivative of my second function, which is going to be negative x. We already found it. So negative x times e to the negative x squared over 2. And so now I'm just going to simplify. So I get 1 over the square root of 2 pi, and then I have e to the negative x squared over 2 as a factor of both of these. And I'm left with a, let's see here, these is going to cancel to be just x squared minus 1. Okay, we typically write our terms in descending powers. Okay, so then for inflection points, I want my second derivative to equal 0. So when f double prime of x equals 0 implies that this whole mumbo jumbo stuff, so 1 over square root of 2 pi, e to the negative x squared over 2, x squared minus 1 has to equal 0. And so that equals 0 when any of the factors equal 0, since it's in factored form. So I get that when e to the negative x squared over 2 equals 0, or when x squared minus 1 equals 0. This has no solution because it has a asymptote at 0. And so then here I get that x equals plus or minus 1. So then I have inflection points at plus or minus 1, so I'm happy. Great. And here's a picture of that graph. So when you learn statistics, you'll be a little bit more familiar with this standard normal distribution probability graph, which is going to be used all the time in stats. We're not really working with it much this year, but I thought I would show it to you so you kind of get to see the functions you'll work with if you ever take stats. Exciting. Okay, next problem. Oh no, got to talk about integration rules. Yay! All right, so integration rules are e to the x dx equals e to the x plus c. And if we have u as a function of x, then my integral of e to the u du is going to equal e to the u plus c. Okay, so let's try a few examples. So find the indefinite integral. Our first one is 5x times e to the negative x squared. So a lot of these you're going to use u substitution if you have multiple functions of x going on. So typically you're going to use the function with the higher degree as your u so that you can cancel when you find that derivative. So I'm going to let u equal negative x squared. Then du dx is going to equal negative 2x. And if I solve that for dx, I get dx equals 1 over negative 2x du. And I'm going to substitute that back in. So now I have the integral of 5x times e to the u, because I switched that out, and then dx was 1 over negative 2x du. So then my x's will cancel. I'm going to pull out my constant, so I get a negative 5 halves in the front, and then my integral is going to be eu du, which is really easy. And so then I'm going to get that this is going to equal negative 5 halves eu plus c, and then go ahead and substitute back in my x. So I had u equals negative x squared, so I get e to the negative x squared plus c. All right, great. Let's try the next one. Next one, integral of e to the 1 over x squared dx. And so for this one, I don't think it matters. Well, yeah, I'm going to let u equal 1 over x because when I find the derivative, it's going to cancel with the x value on the denominator, okay? So then du dx equals negative 1 over x squared. So there's my x squared, which is going to end up canceling with that other x squared. So then I get that dx equals negative x squared du, okay? So then when I substitute this back in, I get e to the u over x squared times negative x squared du. And then my x squareds cancel. And I get negative e to the u, the integral of negative e to the u du. So then I get negative e to the u plus c and go ahead and substitute back in. So negative e to the 1 over x plus c. How exciting. All right, next example. Flying through these. How exciting. Next example is very similar. So we have sine x times e to the cosine x. Just thought I would mix it up and put some trig in here. So I'm going to do the same thing I did before where I'm going to let u equal my exponent because the derivative of derivative of cosine is negative sine, so that'll cancel. So du dx equals negative sine x. So then we get our good old friend dx is negative 1 over sine x du. And that's going to end up canceling with this sine x. So then I'm going to end up with e to the u du, and we get a negative in the front. And so then when I take my integral, I get e to the u plus c, negative e to the u plus c, excuse me. So my final answer is negative e to the cosine x plus c. All right. And I think we have one more example. One more example is a definite integral. Yay, definite integrals. All right. So for this one, we have the definite integral of 0 to 1 of e to the x over 1 plus e to the x dx. And so I'm going to let u equal the entire denominator. So 1 plus e to the x. So du dx is e to the x. So that's handy. That'll cancel. So then I get dx equals 1 over e to the x du. If you like writing it all out, you're welcome to. So then I'm going to go through and substitute. So I have e to the x over u times 1 over e to the x du. All right, so here's something you need to pay attention to. When you're doing definite integrals and u substitution at the same time, keep track of which variable your values are in, okay? So right now I have two variables. I have a variable of x and I have a variable of u in my integral. So when I write my bounds, if I wrote 0 and 1 right now, someone might assume that that's u equals 0 and u equals 1, but it's not. Those are still x values. You could plug them in to this and change them to u values if you wanted to, but if you're not going to do that, because I'm not going to do that in this example, I'm going to write x equals 0 and x equals 1 so I remember, and it's clear to your teacher, me, what variable they are in, okay? And it also helps when you evaluate it later on. All right, so now we get the integral from x equals 0 to x equals 1 of of 1 over u du. And so then when I integrate that, that's the natural log of u, which we know is 1 plus e to the x. So I've switched back to x. I also didn't put the absolute values because this is always positive, so we don't need those. And then plus c. Oh no, we don't do plus c because it's definite integral. So I'm evaluating that from 0 to 1. Now, because everything is back in terms of x, I don't have to write x equals. Okay, so then I plug in the 1. So then I get natural log of 1 plus e minus the natural log when I plug in 0, which is 1 plus 1. So then I get the natural log of 1 plus e minus the natural log of 2. So that's my exact answer. I expect to see your simplified exact answer right above your approximate answer, which is 0.620. Okay. Typically we do 3 decimal places. Okay. I don't remember what the AP test is. I think it's 3. All right. That is all for the video today. You are welcome to start working on your homework.